All right, everybody, we are back, and I'm going to be continuing on with a lecture from the previous video. So in the previous video, we were talking about the basics about how all this stuff's come from. As you can see, we talked about what resistance is, its opposite, which is conductance, reactance, and its opposite is acceptance, inductance and admittance, and where we get those things from. Using a basic circuit, things like that. Apologize for the scrolling. I'm just trying to get my bearings back in as we get going again. Okay, so in this one, what I'm going to be doing is I'm going to be going through a couple of circuits. We're going to go through a bunch of series circuits first, going through a lot of the explanations of them, just kind of working everything out piece by piece by piece. Again, as we get going, I want you guys to be remembering these things, and if you need to pause the video, rewind, that's what they're here for. That's what they're available for. If you do have questions, make sure you watch the video to the end, write down your questions that you have. Hopefully they get answered as we get going. But if you do still have questions, like I've said before, please reach out to me, email me, call me, text me, whatever you need to do, and get these answers in. And again, like I said, I'm going to have these videos posted on YouTube, and we will just kind of go from there. I'm going to break this up into a couple more parts than I originally said in my emails. So this first section I'm going to do, it may be a little bit of a longer video, but I feel it's okay. We're going to go through series circuits, and then we're going to start adding on a few extra pieces to the end, so we have quite a bit of circuitry to go through. And then in the next video I'm going to do is going to be just parallel circuits, and then I'll do a separate video after that where I do series parallel. And so I'll have a couple examples in each of those. That way we can go through and continue to learn what we need to do. So with that being said, we're just going to kind of continue on with where I left off before. If I can find the right page in my notes. Aha, there it is. Okay, so basically what we're going to do is we're going to kind of go through a circuit step by step. We're going to solve for everything, and in the end we're going to use Kirchhoff's to be able to verify that everything still works just like we've been doing it before. Now we are going to be getting into the phase angles, so with the phase angle math we're going to be doing a bunch of conversions. I believe for these first couple ones I have everything written out step by step by step by step. And to be able to show what we need to do. Worst case scenario, like I said, if we do get behind, or if you do get behind or need to ask questions, you can rewatch it several times and go from there. And like I said, please feel free to ask questions. Again, I will be having the Zoom meeting getting going for our normal class time. So when we get back after we're back from spring break, which will be when you guys are watching this, obviously, I was working on this for the week before our actual spring break. So that's why if I say kind of things that are weird, that's why I'm recording them now beforehand to get them ready to go. But either way, I'll have our normal class time from 1 to 3. I'll set up Zoom meetings. That way we can all get on face to face and we can talk and we can get going with any help that you guys need or that you might, questions like that will be live. That will be dedicated time that I will be available. And like I said, you can get answers there or you can get answers by asking me directly. So either way you want to do it is fine with me. All right, so let's go ahead and get started. So we're going to start off with our basic circuit. So we have our AC generator, we have our resistor, we have our capacitor. Now when we're doing these ones, before we get into the next topic, it does not matter which direction you put the resistor or where you put the capacitor. Both sides are fine. The order of them will matter once we get into, I believe it's topic 4, when we start talking about filters. So like I said, you'll see me flip these back and forth. It's because right now it does not matter where things go. So we're going to start off. R1 is going to be 16 ohms. Our capacitor 1 is going to be 4.7 microfarads. Our generator is going to have 6 volts peak, and we're going to have 5.57 kilohertz for our frequency. Now what are we looking for? Well, let's find the given. We want to solve for our X of the reactance for our capacitance total. We want to find our impedance total. Now remember, the impedance is the combination of our resistance and our reactance. Our reactance total is just the values of the capacitor itself. We also want to find our I total, and we also want to find their associated angles. And we want to find the voltage across capacitor 1, and we want to find the voltage of cross capacitor or cross resistor 1. And then we're going to do our KVL, Kirchhoff voltage loop, to be able to prove that everything is still working. We're still only dropping the 6 volts, so on and so forth. All right. So the first step we need to do is we're going to solve for our reactance total. So in this case, we only have one capacitor, which is just C1 right here. So that's the only thing we have. So it is X of C1 is equal to our reactance total, which is equal to 1 over 2 pi times the frequency times capacitor 1's value. So that comes out to be 1 over 2 pi times 5.57 kilohertz and the capacitance of 4.7 microfarads. That total value comes out to be 6.079 ohms, okay, at negative 90 degrees, because remember it is a capacitor, and remember our relationships. This is our R, which is at 0 degrees. This is our X of C, which is at negative 90 degrees. And this is our X of L, which is at positive 90 degrees, which we'll be talking about next week. All right, so we have our capacitance for we have the reactive capacitance for capacitor 1, which, like I said, is also our total. So that one we have is done. Now remember, we want to box our answers so we can come back and find them later. And that way, when we're solving these things, we're making sure we follow along. Okay, now the next step we want to move on to is finding our Z total. It is the total impedance, the total resistive nature of the circuit to AC. So the way we're going to do that is we're going to look at our Z total. When we have our Z total, remember that it is going to be written by the total resistance. So it's going to be our R total plus or minus the reactance total. Okay, whatever the circuit may be, inductive, reactive, inductive or capacitive, either way, we're going to follow the same format. So remember, we have these conversions. If this is at 90 degrees, this value here is going to translate into, so the total impedance of capacitor 1 has 0 resistance and minus 6.079 ohms. Okay, that's its value. So remember, we have R, and in this case, it's going to be minus X of C because we're at a negative 90 degrees. So that is the impedance total of the capacitor 1. The impedance total of resistor 1 is 16 minus or plus, doesn't matter, J of 0, because there is no reactive component to it. So we can leave that at 0, leave it off. But in this case, I like to include it so we can see what we're adding. And up here, I forgot to add my J as my designator, just to indicate that it is a different value and we can't directly add them. So I apologize about that, and I've got that fixed now. So now we have these two values. So one of the things that I've said before is when we are looking at these problems, we want to make sure that we have our impedances in polar or rectangular notation, depending on how we're going to use them. So in this case, with the reactance of capacitor 1, this value up here is in polar notation. So that is great when we're doing multiplication and division. It makes things really easy. But if we're adding and subtracting, we want it in this value. And the reason we're going to add and subtract is because of right here. We have our resistance total plus or minus the reactance total. So we got to look at these two values and we're going to add them together. Just like when we were doing simultaneous equations, we're going to add like values together. So we're going to add our resistances together. We're going to add our reactances together. That's going to be important too, to note that that's how we're going to solve circuits when we add in resistors with capacitors and inductors all into the same circuit. So in this case, we're going to come back to find our Z total. So our Z total is going to be equal to the impedance of our resistor plus the impedance of our capacitor. Okay, so Z total is going to be equal to 16 plus J of 0, and we're going to add that to 0 minus J of 6.079. Okay, so again, we have resistance, resistance, we have a reactive, reactive, or imaginary, think of it that way, And so we end up with our Z total is equal to 16 minus J of 6.079. So that is the total impedance of this circuit, because that's all there is in the component. We have one resistor and we have one capacitor. So that's what we end up with. Okay, now we need to continue on. So we now have our Z total and we have it in rectangular notation. One of the things that we need to look at is that where we need our value? Do we need to change it? So in this case, we are wanting to solve for IT. Now the formula for IT is voltage total divided by resistance total. And in this case, remember, because we're dealing with AC and we're dealing with reactive components, it's the voltage total divided by the impedance total, the total resistance and opposition to AC current. So in this case, we have here, this is division. So therefore, we need Z total to be in polar notation. Okay, how do we do that? How do we convert this guy back and forth? It's not as simple anymore, because if we have a value that's plus 0J, then we know it's just pure resistance, and that's going to be at 0 degrees. If we have 0 resistance and we're given just a J value, we know that it's going to be just capacitive reactance or capacitive inductance, depending on if it's plus or minus. But in this case, we have the two of them. So what do we have to do? Well, the first thing we have to do is we have to convert our Z total into polar notation. And I apologize, I lost one of my pages of notes. Okay, so with that, we need to convert our polar notation. This might take me just a little bit longer to get going, as now I have to find my calculator. I had everything written down, I do apologize. There we go, there's our calculator. So the first thing that we're going to do is we're going to look at our value and we're going to convert this. Okay, so we know to go from in polar notation, it's equal to our impedance at an angle theta. Now, the impedance that we're going to get is going to be the real value squared plus the J value, or our reactance value squared, times the square and the square root of those two added together. Now, remember, we are adding these together, but the thing is, we have to remember, whatever our reactance value is, positive or negative, when we square it, it's going to become positive anyway. So that's why we can get away with just saying plus that value. Because if we have negative 6 squared, it's going to equal a positive 36. If we have a positive 6 squared, it's going to equal a positive 36. So like I said, either way doesn't matter. So then to get our theta, we also have to go back and look at our triangle. Okay, so this is our axis. This is going to be the angle. There is our values. So there's our impedance. There is our reactance values. And this is our resistance value. And we're looking for this angle right here. So again, we have the tangent of theta is equal to the opposite over the adjacent. Because we have those two values, that one we're going to calculate, so we don't necessarily want to use that. We want to use what's given to us as much as possible first. So in the end, we have our theta is equal to the arctangent or inverse tangent of the opposite over the adjacent. Okay, so now we can convert this value. So we're going to take 16 squared and we're going to take 6.079. We're going to square that value. Now we take the square root of that. That is going to give us our Z value. So we'll plug it up into our calculator. So we take 16 squared plus 6.079 squared. That's going to give us that value. Then we take the square root of that value, and that gives us 17.116. So 17.116 at, now we need to do the second part. So theta is going to be equal to the arctangent of the opposite, which is our reactive value. So it's going to be, and this one we do want to use the the negative because that's what it is. So, because remember, it's down here in this quadrant, which means this is a negative x. So we do the negative 6.079 divided by the positive 16. And theta then comes out to be, when we plug this into our calculator, so we take the arctangent of negative 6.079 divided by 16. And there's my problem right there. Need to make sure I'm in degrees. That's going to be one thing that comes up. So that answer was correct. It was like 0.3 something rads, but we want it in degrees. So I'm also going to put this into engineering mode, and I'm also going to give me 3 decimal places. That's what those settings are. So right there, that's what I was saying, that one is in radians. So it's 0.363 radians. Now, let's redo this again now that we're in the correct mode. Negative 6.079 divided by 16. There we go. That's a little bit closer to what I was expecting. Because remember, whichever the value is greater, your resistor or your reactive component, that's going to what dictates, where the degree is. If your resistor value is bigger, it's going to be getting closer and closer to 0 degrees. If your reactance value is bigger, it's going to get closer and closer to the negative 90 degrees. And if they are exactly the same, then we're going to be at a negative 45 degrees. So that way you can kind of check and see what your answers are. Because like I was saying with this one, I knew immediately that value was wrong because it was not. It shouldn't be a decimal that small, because this isn't, there's still, about a third of that value. So we should be getting, a third of 90 degrees. So we're close to it. So in this case, we've got, slide this up a little bit, and we have a negative 20.804 degrees. So our final Z total for this circuit in polar notation is 17.116 ohms at 20.804 degrees. And now that we have that converted, now we can continue on and solve for the rest of our values. When you're doing the homeworks online, you'll have to look to see how they want these values. Most of the time, they're going to be in impedance, or they're going to be in polar form, so you're going to want the total magnitude of it and the angle. And it's just easier to put in those answers in this format. Like I said, most of the time we're going to be using everything in polar. When we have to add and subtract things, that's when we want them in rectangular. Okay. So now that we have our impedance in polar, we can continue on. So I'm going to hide this guy for now. I'm going to move him off my screen, and I'll bring him back as I need. So now that we have this impedance value, we're going to go back through and we're going to solve for our currents and our voltages. So our current total, as we remember, it's equal to the voltage total divided by the impedance total. So we have 6 volts peak at 0 degrees. Remember, if we're not given an angle on our power supply, we just assume it's 0. And we're going to divide this by 17.116 at negative 20.804 degrees. Okay, so we run through the math on that. Our total is equal to 350.57 milliamps peak. And the reason we are doing that is because we just want to make sure we're registering what it is. We're not in RMS, we're not in peak to peak, things like that. And then the angle is going to be 20.804. Because remember, this is going to be 0 minus a negative 20.804, which gives us 20.804. Remember the powers of 10 rules when we're dealing with the degrees, and we treat them just the same. When we divide, we subtract. When we multiply, we add. Okay, so there is our current total. Now we want to take that value and we want to find our individual voltages across these guys. And this is what we're going to be measuring on the scopes. And we'll go through in a little bit too to find out how to solve for those values when we're measuring them. We'll talk about that more in the lab time in those instances. Okay, so now we're going to look for the voltage across resistor 1. Now, if we look back in original circuit, remember it's just a series circuit. So the current is going to be the same for both of these components. So now we come back to our VR1. So VR1 is equal to IR1 times the resistance of R1. Okay. So we have 350.57 milliamps. At 20.804 degrees. And then that's going to be multiplied by 16 ohms at 0 degrees. So when we run that through our calculator, we end up with 5.609 volts peak at an angle of 20.804 degrees. Because again, remember, we take the 20, we add 0, that's what we end up with. So VR1 is equal to this value. Now we want to find the voltage across capacitor 1. So we're going to do it the exact same way. Voltage across capacitor 1 is equal to the current in capacitor 1 times the reactance value of capacitor 1. So we have the same current because it's a series circuit. So 350.57 milliamps peak at 20.804 degrees. We're going to multiply that by the reactance, which was 6.079 ohms at an angle of -90. Now we multiply those through and carry everything through, and the voltage across capacitor 1 is equal to 2.131 volts peak at an angle of -69.196 degrees. Again, we just multiply the 350, the 350.57 milliamps by the 6.079. That gives us this value right here. And then for the angles, we have the 20.804. We're going to add a -90 to that, and this is the difference that we have. So there is our final value. So now if we come back up and look, we have found the impedance total, we found the current total, we found the voltage across capacitor 1, we found the voltage across capacitor or resistor 1 as well. Now we need to do our double check. Make sure that did we do this right, because those numbers seem kind of odd. And if you look at them, they are a little bit odd. So if we have the 5.6 volts and we add 2.1 volts to it, that gives us 7.7 volts. Well, how can that be? Because we only started out with 6 volts. The difference is that these two guys are out of phase. And if you look, they are 90 degrees out of phase. Our resistor is sitting at 20 degrees. The voltage of the capacitor is sitting at -69 degrees and change. We add those together, we're going to end up at a 90 degrees. So the cool thing is this 90-degree angle is going to be maintained the entire time, not even just for the resistance and reactance values, but for the individual voltage drops as well. So that's the cool thing is your angle should always add up to be 90 degrees apart from each other with a resistor and a capacitor, and then also with a capacitor and an inductor. An inductor and a resistor. And then later as we come in and find out that the capacitor and the inductor are going to be 180 degrees out of phase when we start looking at those guys. So another little things that we can check to make sure we're on the right path. Okay, so now what we need to do is we want to use our KVL, because we want double check to make sure that this still holds true, which it will, and to double check that we have our values right. So remember, for our Kirchhoff voltage loop, it's going to be everything in a loop. So if we come around and look, we can start down here to our ground and work around, and we'll draw our equation. So what we have is we have -6 volts plus the voltage drop across R1 plus the voltage drop of capacitor 1 has to equal 0. Okay, same Kirchhoff voltage loop that we've been doing. So in this case, our equation is going to be 6 volts is equal to VR1 plus VC1. Now we can go back through and we can add these values back into, substitute substitute this value in, and substitute this value in, and then we can solve. Okay, so we have 6 volts is equal to the voltage of resistor 1 is going to be 5.609 at 20.804. Then we're going to add to that the voltage of the capacitor, which is 2.131 at negative 69.196. So now when we're looking at this, remember what I said before, if we're going to add and subtract values, we need them both to be in rectangular notation. So we're going to take this value, we're going to convert it into rectangular. We're going to take this value, we're going to convert that back into rectangular. And then we're going to add those values together and show what we got. So remember, we're going to come back to our triangle. We have our real value, we have the reactive value, we have the total, the impedance, and we have this. And so we also are going to use this generally as the total value for whatever we're looking for, the magnitude of this polar equation. So as we go through this, and remember, we have these following formulas. We have the SOHCAHTOA. So when we're looking at this value, again, we are in polar notation. So we have this value and we have this value. Well, we want to be able to find these two guys. Well, we don't have our opposite value. We don't have both of them, so we can't use tangent. So tangent's out. But in this case, we have the sine of our angle, we have our opposite, we have our adjacent. Sorry, this should be A, not O. And we do have the hypotenuse. So we'll be able to use this equation and this equation because we have 2 out of the 3 that we need. Okay? So when we're coming in here, we're going to solve for the imaginary value. And I'll show these steps down here. So we want to solve for the imaginary. Or we'll solve for the real first. Either way, it doesn't matter. So when we start with this, we know we have our R over our Z, because we know we're going to use one of these. So we're going to use either the opposite or the adjacent. And in this case, our real is the adjacent. So this is what we need. We're given this value. And that's going to be equal to the cosine of theta. And in this case, we're also given this theta. So we're going to move everything across. We're going to multiply both sides by z, which is in this we're using as our magnitude. So z over here, we're going to end up with an r is equal to the cosine of theta times z. Or another way to look at it, it's going to be z cosine theta. Okay. So now we're going to plug the values in. So we're looking at this guy first. So I will show the math for this one is in red, and the math for this one will be in green. That way we can keep things straight. So we're going to also solve for the imaginary. Because remember, we are at an angle, we're not directly at 0 or negative or plus or minus 90, so we can't do an easy conversion. So in this case, what do we have? We have we don't have the imaginary, our x value. We do have our z value, so we need this one. We have this one. So when we look, it's the sine of theta, and this one again is given. So it's just a simple matter of reordering this equation. So again, we're going to multiply both sides by z. That'll cancel it over here on this side. So we end up with our reactance value is equal to our z sine of theta. And those are our 2 equations that we're going to use when we're converting polar back into rectangular. So now, let's switch over and we'll solve these guys. So now we're going to solve for the 5.609 at 20.804. So our real value, come back and look at our equation, is z cosine of theta. So our r value is equal to 5.609 times the cosine of 20.804. So our real value comes out to be 5.243. And in this case, it's volts because that's what we're dealing in, is volts. So now we want to find our imaginary value. So now we're going to take, so remember our formula for here that we found is our z, which is the magnitude, times the sine of theta. Remember, this is all coming from here. This is z. This is theta. So we're going to come back up with a 5.609 times the sine of 20.804. And our imaginary value is going to be 1.992. So this value, those two are going to combine together. And we're going to have, remember we wanted r plus or minus our x value. So in this case, we have 5.243 plus, because this value down here is positive, j of 1.992. So there's that value. Now we want to solve for this next one. So we have 2.131 at a negative 69.196. So the real value, remember, is the z cosine of theta. So we have 2.131 times the cosine of negative 69.196. The real value is going to be 0.756. Then we want to solve for the imaginary value, and that's our z sine of theta, remembering it from our previous equation that we got over here. So the imaginary value is 2.131 times the sine of negative 69.196, and that value comes out to be negative 1.992. So now when we want to combine these guys together, we're going to combine them together into one equation. So we have 0.756 minus j of 1.992. Now, we have these two values together in rectangular notation, which is where we want them to be able to go through and add them together for our Kirchhoff's voltage loop. So now we'll go through and we're going to add these guys together. So we're going to rewrite our equation. So we have 5.243 plus j of 1.992, which is this value right here that we found for the first part of our circuit. This is the voltage of our resistor. Remember, this is the voltage of our capacitor. Just now it's in rectangular notation. Then we're going to add that to our 0.756 minus j of 1.992. Now when that's all said and done, that's going to be equal to 6 volts at 0 degrees. Okay, we haven't worried about converting this one yet because I'm going to show you what's going on, and if we need to, we can convert this guy down. Okay, so we're going to add these together. So we take our real values, we combine them together. We take our imaginary values, we combine those guys together, and what we end up with is our 6 volts at 0 degrees is equal to 5.999 plus J of 0. So remember, if we have a J that's equal to 0, that means our angle is going to be 0, and this is going to be our magnitude. So we have 6 volts at 0 degrees is equal to 6 volts, well, with our numbers, 5.999 at 0 degrees. Those are equal. It's close enough for all intents and purposes. The 5.999 just comes down to rounding and how those things that we did there. So like I said before, when we start getting to the AC, our margin of error is going to be opened up a little bit because there's a lot of different things and a lot of rounding that can happen. So we end up with this. Our values is equal to. We started with 6 volts. We ended with 6 volts, dropped across the rest of the circuit. So here we've just proven that our Kirchhoff voltage law still applies. And it works. So with that, that's one of the easiest ways we can do it. So we're going to go through, we're going to solve everything. We're going to basically the whole idea is we're trying to get our voltage drops across the whole circuit with just this basic circuit right here. And we go through, we solve our reactance first, then we solve into our impedance total, which in this case is just adding everything together. We find our total current, take that total current, multiply it by each of the resistance and the reactance values to get the individual voltage drops, and then, which is what we've done right here, and then we come back to our KVL, we add those together, and we add and do conversions as much as possible, as much as we need to be able to get the values to either add them or subtract them back and forth. So with that, I'm going to kind of do a little bit of a recap, and then we'll do some more practice problems. So feel free to go back through and replay any of these sections as you need to. And then the next little bit is going to be just a couple more problems that we're going to run through the exact same thing that we did, so you guys have several examples to be able to reference when you're working on these for the homework. And like I said, please, take notes, ask questions, and let me know if you need me to explain something again. This is going to be a learning progress, and it's going to be difficult, but we can get through it. I know we can. We're all smart enough people. We all know what's going on, and we shouldn't have any problems. Okay, so I'm going to switch colors real quick. So we have our recap. Okay, we want to use rectangular notation to add and subtract and we want to use polar to multiply and divide. To help us in that, we have these trigonometric identities. So the sine of theta is equal to the opposite over the hypotenuse. We have the cosine of theta is equal to the adjacent over the hypotenuse. And we have tangent of theta is equal to the opposite over adjacent. Our triangle, this is our real, this is our x of c, or our imaginary. This up here will be x of L when we get into it, but these same principles still apply. Our R value is here, our x of c value is here, theta is there, and the total impedance is there. To go from rectangular notation to polar, which is to say R plus or minus j of x to a magnitude at an angle. Z is now going to be known as square root of R, the square of R plus the square of x, the quantity of that squared. Theta, we're going to find in reference to our triangle over here. So it's going to be the inverse tangent of plus or minus x, whatever it may be, over R. And that's going to give us this conversion. Now, if we want to go backwards, or not backwards, if we want to go the other direction, if we want to go from polar to rectangular, we're going to go, again, looking at our triangle and figuring out what we have. It's going to be, the real value is going to be equal to the magnitude times the cosine of theta. The imaginary, or x, is going to be the magnitude times the sine of theta. And we can go back and forth with these all day long. Okay. Then we also need to remember that when we're finding our resistance total, it's going to be voltage total divided by current total. And in this case, we're looking at total impedance of a circuit, not just resistance. So remember, impedance is the combination of resistance and reactance. So these two are equal. Oops. And that will be equal to our Z total. If we're looking for current, remember the formula for current is voltage divided by resistance. Or I total is going to be equal to the voltage total over the impedance total. And then the same thing for finding voltage. It's going to be the current total times the resistance total. Or voltage total is equal to the current total times the impedance total. We can use those interchangeable. And then the last thing to remember is we have some quick conversions. Okay, if we have an angle of 90 degrees, that's going to translate into a positive J value. If we have a negative 90 degrees, that's going to translate into a negative value, a negative J value. And if we have 0 degrees, that's going to translate into our real value. So remember, if we have something that's at 90 degrees, it's going to be a 0 plus J. If we have a negative 90, that's going to be a 0 minus J. And if we have a 0, it's going to be an R plus 0J, or minus 0J, whichever one you prefer to use. I end up usually using positive J just because it makes it so we don't have to deal with those negative numbers a lot. And we can convert these guys back and forth. If it's an angle, if it's any angle besides these three, then we have to go through and we have to use this polar to rectangular conversion. There's no quick way to do it. Again, with these guys, if we have only a positive J value, then it's 90 degrees. If it's a negative J value, it's a negative 90. And if all we have is an R, it's that. It's a 0 degrees. So this would also be equal to a this would be like 0 plus J of some number. This would be 0 minus J of some number. And then this would be some number plus J of 0, just as a reference. So we can go back and forth between those guys everywhere. There's the three cases that it makes it really easy for us to find. Okay, so that's it for as far as the actual notes and the review goes. The next part we're going to do is go through several examples of just series circuits. So we went through one example. Now we'll go through a couple others and we'll add some more things. We'll change values up. And then, like I said, the next video I'm going to do is we're going to do just the polar. So I will go ahead and end this one here. This will give us the examples. And then the next 3 videos that we're going to have are going to be the series RC circuit practice. We're going to have parallel RC circuit practice. And then the last one is going to be series parallel RC circuits.